Hi everyone. In this set of videos, we are going to discuss three special types of trees. Over the past 2 weeks, we have been discovering different non-linear ordered data structures that includes trees, and we covered first n-array trees, followed with binary trees and binary search trees, and then finally we discussed AVL trees. So in the last set of videos, we discussed that BSTs have a performance issue whenever we are trying to add elements that are in some order. The trees get more splintly and they basically have a time complexity of O of n in the worst case. We fixed that problem using rotations, and we also discussed the AVL trees, which is kind of like an algorithm that uses these rotations to fix the issue of BST performance in the worst case. So today we are going to cover three other types of trees which also like fix that problem of accessing an element in the worst case in BSTs. So first one is B trees. We are going to cover the properties as well as how we insert elements into a B tree. We'll also discuss some of the use cases where these three data structures that we are going to discuss are used. We'll finally compare the difference between B trees and B plus trees. Then we'll start with another data structure called splay trees, discuss its properties, and finally we'll terminate the lecture with red-black trees, covering what are the properties and how insertion works in red-black trees. So the core problem that we discussed last week in BSTs was this problem of height imbalance, which is if I have some numbers in sorted order, like in this case I have 25, 51, 65, 85, and 91, our tree would look something like this. Now here, the insertions are not in a random order because like this is a sorted insertion. So you can say that it is not random. And you'll find this use case like whenever we are trying to build a tree, like in our software applications, you'll find this case a lot, which is like, let's say if you are creating some uh, data management system or you are basically keeping a track of employee IDs. Let's say a new employee comes up and joins the organization. You'll see that, or a new customer goes to a bank and opens a new bank account. So let's say the previous IDs of the employees was 2501. Let's say 100 new customers opened their account in the bank this particular month. So the new IDs would look something like 501 to 502 up to 600. And whenever we try to insert that in our existing data structure, that will lead to height imbalance. So how we can fix that, we discussed first way of fixing that by transforming the tree from our splinty tree to a bushy tree using tools and algorithms, which is we transform the tree through rotations. The second way we are going to discuss today, and that is basically the motivation behind our first data structure, which is B trees. So here, instead of like rotating our data structure, what we basically do is we alter the structure by design, which is, let's say if I try to insert a number 100 in this new tree, instead of adding a new node on the right of 91, we increase the size of the leaf node. So let's discuss a particular use case, which is, let's say if we are trying to insert these numbers in this tree, our tree after it has been created would look something like this, which will again cause an imbalance in height, and it will keep going. So instead of basically appending it to the leaf node, we increase the size of the last node and inserted all elements in it. So what would be the pros and cons of this approach? The first con of this approach is it can lead to overstuffing. And what I mean by overstuffing is, let's say if there are a lot of elements in this root node, in this leaf node, then let's say if we were trying to search 135, we search 135 and compare it with the root node. We go towards the right, we saw that 135 is greater than 85, and then you are going to have to perform some linear search or a binary search here. So at the end of the day, we just got back to like O of n complexity. So that is the con of this approach. The pros is it is still following the BST property, which is, if you see, like on the left, we have all values that are smaller, and on the right, we have all values that are greater. The second pro of this approach is we have a better balanced height. Like if we followed the other approach, we basically didn't had a balanced height because it was supposed to skew the entire tree. But now, since we increase the size of the node, we have a better balanced height. So let's try to fix this issue, which is like it didn't fix the non-random insertion, but it did fix the height imbalance problem, which is now the height is more consistent. But still, like if we have non-random insertions, our leaves will start to look more overstuffed. So how we can fix that is by placing a cap on the number of elements that are structurally present in a node. So basically, we set a limit L on the node filing, which is you cannot have more than L nodes in one, L keys or L values in a particular node, which is in this case, let's say if we do like L equal to 3, there cannot be more than like 91, 100, and 101. After that, like if we try to insert, something else must happen. And that is basically the gist of what we are going to see in our first data structure, which is BST. So it adds additional rules to ensure that if our nodes get overstuffed, how we can prevent that and make it more balanced, which is we get the best of both worlds, which is we have a balanced height, also we have a consistent BST. And we are going to see that in our next video.